are live.
Hi, everyone. Welcome to another Wolfram Institute live science stream, where you can basically consider this a part two follow-up of a meeting that we began yesterday. So we're going to be discussing with Carlos, with Nick, and with Richard this work that we're doing on foundations of mathematics. It involves extensive research on hypergraphs and also the development of these things called complexity categories for understanding better emulations between formal systems, the complexity trade-offs that are involved on the algorithmic side and on the behavioral side when you pass back and forth between these various formal systems. So Carlos took the initiative and wrote up a kind of a formal technical document on hypergraphs, but not just hypergraphs, on hypergraphs and how they fit into this categorical framework and how they fit into this, I guess you could call it complexity study. And so we began to discuss it yesterday. We ran out of time, and I was surprised to learn that Nick had developed a Packlet about hypergraphs as well. This is, for those of you who are beginning to understand Nick, this is kind of Nick's MO. Just surprise you with either surprise you with things that he's done or yeah,
No, it's
other
just
various kind of
it's just a few
surprises.
functions. It's not
Yes,
like
and
you develop a Packlet thing.
he's very modest as well. Yes, yeah. But it's something. It's something to discuss that's relevant to what Carlos has. So why don't we begin with you, Carlos? You probably remember where we left off last time.
Yep.
Let's continue.
Okay, so let me share here. I'll put our faces nicely for the stream. Let me hide.
Ah, yes. Yes.
This Zoom, this is so frustrating. Okay, just touching up the screen for the viewers. Okay, that's about right. So, yeah, I actually wanted to, before moving on to the later stages, because Nick did have some comments, and now that we've learned that he has developed this start of a Packlet, we can maybe discuss briefly how you're thinking in terms of these operations, because it seems to me that if we're going to do hypermatrix approach to, or hypermatrix definitions of things like degrees and degree distribution, and try to generalize notions from standard graph theory into this hypergraph theory context, we might want to understand, if you have some particular preferences or thoughts, and also Richard, regarding what kind of operations we're going to do, and because you seem to be, yesterday you seem to have some questions about precisely what we are doing, and we were citing offline before that you've been discussing sort of index contraction and so on. So if you had some thoughts or questions or comments, I thought it might be better to sort of front load them now, and then I'll go into the second half of the document and the structure there, because there is less, it's less filled. This is much more settled theory that I am kind of confident about, and it will be better to go back and forth a little bit with your thoughts on tensor contraction, quote unquote tensor array contraction, whatever.
No, it's not relevant here. It's just, I just mentioned it because it's not relevant to hypergraphs, even though there is a adjacency tensor function that I made that makes a tensor version of an adjacency matrix for hypergraphs, and it works different than one in the resource repository. And that's why I'm mentioning. But this is like yet another representation of a hypergraph as a matrix. We have three now. It's like we have an incidence matrix, which is a matrix. We have a hypermatrix, which is graded matrices, and we have a tensor thing, which is an adjacency tensor, which has
What do you mean by tensor? Just an higher order array?
As an actual array. Yeah, it's just a array of a rank with the highest order of a hyperage that we have. If you have the highest order of a hyperage is 3, then your tensor going to be rank 3 tensor.
Hey Nick, are you sure that you're using your earpod microphone? Because your audio sounds harder to understand than usual. Yeah.
I'm struggling.
No, I'm using a different one. I don't know. I have like an actual microphone now. Maybe it's bad. Or
It's
maybe
bad.
I'm not speaking into
Yeah.
it. Or it's not set up.
I mean,
Nice.
right now I'm hearing fine just now, but
No, it depends where it's like how do
That's
I speak,
better.
I guess.
Yeah, that's better.
Yeah.
Yes.
Yeah.
maybe
It's just I
project
should
more
speak
into it.
into it, not
Yeah.
yeah. It's just
Okay.
I figured it out.
All right. Cool. So, well, in that case, let me just briefly recap where we were. So I was discussing the fact that there seems to be a huge freedom in how to define operations on these arrays, higher order arrays. But what you want to do is you want to we are motivated by these arrays being representations of hypergraphs or being some kind of redefinition of hypergraph, equivalent encoding of hypergraph. So for example, let me just say this particular expression here, right? The way you read this, right, is you understand. Okay, maybe that's actually this is the better example, the one that I spell out here. So imagine that you have a pair of conventional graphs, A and B, right? And so A, X, Y, and B, Y, Z are just their usual adjacency matrices, right? And maybe they're simple and there's just Boolean values or whatever.
Okay.
So the distinction the kind of primitive notion that I want to put forward that seems algebraically natural, but is also very well justified on the graph side, is this idea of the incidence product, right? So the incidence product is basically this condition. Now, if you read this from a purely algebraic point of view, you might be thinking, all right, so you're just putting together two indices and you're not summing over those indices. You're just saying y, but there's no sum over y, right? So what this means in a Boolean algebra sense, or in a kind of more strictly hypergraph or graphic sense, is that you're saying, look at vertex X, look at vertex Y, and look at vertex Y and look at vertex Z, and you're checking for the conjugation of the existence of of an edge on A and an edge on B, precisely in this topology, right? That's why you're doing an AND, right? You're doing a conjugation of these two. So because we're interpreting these as Boolean variables right now for convenience, for clarity of explanation. These are checking for exactly the pattern, A, B in this sort of V shape, right? So the Boolean function that we get out, right? If you think about it as a Boolean function, is a Boolean function that takes three vertex arguments, right? Takes X, Y, and Z, and it checks for whether there is an A edge from X to Y and a B edge from Y to Z, right? So the information that is contained in this, what I call I here, is a cubic adjacency matrix, so to speak, right? It's a Boolean function that has a range over three variables. In this case, the variables are the indices, right? So that thing, so that's why this particular product, this particular way of taking product, which is what we call an incidence product, is very, very natural when it comes to hypergraphs, because it's directly probing the topology of a given graph just by using conjunction and disjunction, right? So here, what you do is you say, well, instead of checking precisely the topology X, Y, Z, that you want to find exactly a V topology in that X, Y, Z vertices, what you say is look at X and look at Z and just say, are there any at all Y's such that the topology exists? And so in this kind of sense, you Boolean sum over all of Y, right? And you keep, if you get one hit, you keep it, right? So this is a contraction, right? This is what it means to do a contraction. So I think this picture is very important to keep in mind, because when we're used to linear algebra, you think of contraction as some kind of inner product, and you start to get all these geometric intuitions about inner product and so on, and that's interesting to do. But I think at the purely graphical level, the incidence and contraction should be understood in this way, right? It's more about checking a precise existence of a structure, or saying when you sum over, you basically make that topology kind of variable, and you say, can you find some and then you kind of model it.
Yeah.
Right. So anyway, so just as an example for anyone watching, that this is the kind of products that we are considering. And so, wait, did I have a big formula? I think it was a big formula somewhere. Some examples. So the kind of products that you can get out of this. Wait, what were the big formulas? Just to give an example. Well, okay, yeah. So for example, here, right? So you can have several arrays of different dimensions, different sizes, and as long as they have one index in common, here represented by L, right? You can just do this incidence operation, right? We just basically multiply them together, and all you're checking is that if these represent the adjacency of hypergraphs, this just represent that L is a common vertex that kind of lives at the intersection of all these higher order edges, right? From A1, A2, A up to AN are sort of different hypergraphs or differently colored hypergraphs, if you like, right? So anyway, so this is just to emphasize that these operations, they are algebraically natural, but they are mostly motivated by the fact that they represent hypergraph information very naturally, right? That's why we're taking these operations and not others. Of course, they are vindicated by the fact that when you define the adjacency hypermatrix of a hypergraph, you find this is the natural operations, right? I mean, you just restrict for the binary case if you like, and you do graphs, the conventional graphs, and you find the usual, multiplying by the adjacency matrix corresponds to sort of sending densities over the graph and all these interpretations. So all those things kind of generalize naturally as long as you keep this incidence and contraction framework, right, in mind. Okay, so as I said, what I envision hypermatrices doing for us is that they are going to be essentially how we encode the hypergraphs operations themselves, if we are treating them as sort of data structures directly, and if they have, if we have a more efficient way to encode them, as Nick is going to show us later, we will just have to see how that encoding gets reinterpreted or re-expressed in.
Now hold on. When you say operations, do you mean the rewrite rule using this trio of hypergraphs? So what are the operations then?
Operations. So this is an operation. The example that I was using for clarification. This is an operation. This operates two graphs, two hypergraphs, right? These are graphs in particular. So this thing, it's an operation. It's internal to graphs, right? So this will be so this categorical composition, right? So in a category you have composition. So that's a form of generalized categorical composition. This thing here is literal categorical composition in the right category, of course, the category of relations or the category of matrices or whatever. So these are operations in the sense of composition. These are not operations in the sense of taking a rewrite system and interpreting the relations between states as some kind of morphism. So this is how the hypergraph machinery can encode systems like category theory as a particular case. But this is not so much directly speaking of the rules, because the rules are just going to be hypergraphs that are related by some input-output context, whatever framework, right? So this is just to these are the operations of, for example, if you have two graphs, right, two hypergraphs. By the way, if I say graph from now on, I'm going to mean hypergraph. I don't want to fill my mouth with hyper all the time. So if you have two graphs and you want to just additive union them, right? You just want to put them together. So this is an operation that is a very natural co-product in the right category, blah, blah, blah. So these are operations that are primitive to the data structures, which don't show explicitly when we do a rewrite system, because they are kind of at the user end level. Because these are the kinds of operations that you do when you set up your system. You say, these are my states, and you can put two states together just because you can just pick them out, right? So that is mathematically something that needs to be spelled out. And this is the kind of operations that we're talking about.
Let's just make sure I understand.
Yeah.
Hypergraphs are our underlying data structure. Ultimately, we're interested in rewriting on them, but before we can even rewrite on them, and of course we're expressing the rewrites just using different hypergraphs, we have to construct them. And you need operations in order to even be able to build and specify the hypergraphs themselves.
Exactly.
Those are these operations.
Exactly.
But this is in the back of the room.
Correct.
Before we okay.
Yeah.
Okay.
This is just exactly.
These are behind the scenes.
Yeah.
Okay. So these computations, I mean, these operations. This is not okay. These are preliminary operations we kind of need to be able to define before we can even work with a well-defined data structure in the first place.
Exactly. Yeah. This is just
fair enough.
It kind of comes for free.
Yep.
It comes for free with the definition of the structure, right? The moment you define there's no further choices that have been made. Once you set up that your hypergraphs are this definition, all these operations come for free in the sense that if you have sets and multi-sets of edges and all this kind of stuff and the type mixes and all this stuff, the combinatorial species, all that business, there's a lot of structure that comes for free. And so all these operations come for free. It's a matter of choice whether to spell them out or not. So they
come for free, but you'd prefer to make them explicit so that we understand exactly what it is that we're working with.
Yeah.
Is that right?
And that and to make clear that in order to construct, as you said, for example, to construct the hypergraphs themselves, you don't just pull them out of thin air and say, oh, take this hypergraph. But you can say, well, this hypergraph is built as an additive union of this, or it can be built as a quotient of that, or things like that, right? So you have a little bit of data structure behavior that is kind of wired in. But this is kind of in the package of the data structure. We are not thinking of this as something that is going to be computationally kind of encoded, right? In the same way that rules will encode computation. Because these are, by the way, not even labeled hypergraphs, and our encoding is going to work at the level of labeled hypergraphs. Right?
Yes.
So anyway.
Okay. With that understanding in mind, the details of how how should I say this? This kind of audit of these operations and properties that you get for free, and I think we often conveniently overlook because we have functionality where we just fetch these things. This is good. This is diligent. We should have a section in the report on basically constructing or dissecting or really understanding exactly what these data structures involve.
Yeah.
Now, for the purposes of time, though, because we're about halfway through the meeting, why don't we proceed to, like we have the we're describing the kind of the guts of the hypergraph. Okay, we have our hypergraphs. Let's now discuss the kind of the formalism that you have in mind to describe the scope of the study itself, which also involves that too, and you have some here. So let's keep going.
So exactly. So once we have the framework we're working with hypergraphs, the next step is to think of our rewrite rules are going to involve pattern matching. I mean, I think this comes as no surprise to anyone watching, and so one of the earliest approaches that we should take I'm proposing to take is to look at motifs. Now, motifs, in some sense, are building blocks of hypergraphs. If you want to restrict to finitary graphs, hypergraphs, these are basically you can build all hypergraphs constructively with motifs, right? And so this is as simple as saying, well, all hypergraphs are made of hyperedges, and hyperedges are hypergraphs in particular. It's kind of that silly, but the point of motifs is not to just say, well, everything is made of hyperedges and hyperedges are a particular case of hypergraphs. It's just sort of semantics of what you're calling. It's more about the compositionality of these things, right? So that's why these operations of hypermatrices were relevant, and so you can have a systematic way of constructing these hypergraphs. So maybe we don't care so much because we're gonna rewrite anyway, and we're going to regard this as a particular case of our rewriting rules eventually. But the fact of the matter is that the hypergraph rewrite rules require this notion of motif, or at least it's implicit in the notion of motif, right? Because you probably want to just stay parsimonious and say, I'm matching this motif against this motif, and not so much I'm matching this exact sub-hypergraph to something else, because in that case you're basically detecting sub-hypergraphs in your hypergraph and not.
So qualitatively, I can appreciate what a motif is. We use it as a shorthand often.
Yeah.
Do you have a definition?
Yes.
Did we miss? Okay.
So a motif, basically, given a hypergraph category. So whenever we have this
isomorphism
one,
class.
It's an isomorphism class of a typically simple and connected hypergraph, right? And the idea is that connectedness is the common requirement where you can always apply motifs in the disjoint components of a hypergraph and nothing changes. So connectedness is not so difficult to understand, and simplicity is just because if you iterate your motif several times, you get non-simple versions of the same thing. So it's kind of a natural requirement. And so yeah.
Motifs don't actually depend on labels.
No,
right?
We have no labels so
They're
far.
independent of labels.
Yeah, we don't have labels so far. Because these
What would you call these? What would you call these things you have? These numbers you have attached to.
Oh no! This is just an example of motif adjacency. But this is just one example of how to use motifs to do.
Oh yes, I see that. Yeah. Okay,
yeah.
fine. Yep. Okay.
This is not these are not labels. So labels, this is just an example.
Yeah. Got it.
Anyway,
Got it.
So because motifs are going to be at the center of rewrite rules, because at the end of the day you have motif gives motif, in context or where it happens. One of the problems one of the issues that we might encounter is, how do different motifs match to each other, right? Like, because motifs, if they are isomorphism in class, if they really are distinct, which is something that we should think carefully about in terms of the implementation eventually, but if they really are distinct, then they're going. I mean, it's a very strong tool to have to say, well, I have these finite elements of building. This is not like enumerating, but this is more like having a full classification, right? When you really have distinct motifs of increasing size, then you have an actual classification. So here I give some example of particular kinds of graphs and an actual enumeration of these because they were generated. So I say here we can probably do better with Wolfram language.
Yes.
Because I did this a few months ago with Sage and it was fine. It generated all the graphs, but I ran the program again and it took to generate this thing. It took like a day or something. It was very long.
Wow.
Yeah, because it generates it doesn't count. It generates the actual hypergraphs, right? So it generates them all and then counts them. And yeah, some combinatorial people, friends of mine, have looked at the problem of generating these sequences. The sequences didn't exist, so there's this sequence repository. So it's a fun fact that no sequence of 9 numbers of this particular numbers have been submitted. So that's a funny thing. And basically these numbers, just to give a context why I include this example, these numbers are the numbers of motifs essentially, right? Because these are 2 and 3 graphs, so these are essentially binary and ternary motifs, right? Like order 3 or order 2 motifs for this thing. So you can see that it grows incredibly faster when you go up in order, right? Like I don't know, but these 2 numbers are like however many, like 7 or 6 orders of magnitude apart, or 5 orders of magnitude apart. So it's quite crazy. And to think that this is a 9-edge hypergraph. This is a hypergraph that fits in the palm of your hand if you have triangles that are like a few centimeters wide, right? Like there's 15 million combinations that you can put in your hand, and they're all different, right? I mean, this is kind of crazy. So yeah, my proposal is that in this effort, especially if we say, well, let's look at simple undirected hypergraphs, for example, for a while to develop functionality and so on, is that we can actually identify and have some taxonomy of this thing. So the obvious thing to count is size, right? It's an obvious thing to count, size. Just in this case, size means number of edges, right? So 1 edge, 2 edges.
How did you make these, by the way?
This is just graphics. Just graphics.
Okay.
Yeah.
Okay. We could reproduce this probably.
Yeah, absolutely. Yeah.
Actually programmatically.
Yeah, absolutely. Yeah.
So
absolutely. So I did this with a graphic package that I was using for a year or 2, and I feel now that I could actually code this and generate it, like no problem. But for that we should, and this is something I wanted to discuss today if we have some time, which is the generation algorithm that we want to use, and discuss with the functionality that we have already and things like that. Anyway, so that leads directly into the, so if we have agreed some category of hypergraphs, we have agreed that we look at motifs within that category of hypergraphs. I'm suggesting the category to be simple and directed to begin with, and I'm suggesting to do this size metric, the overall metric. Then the natural thing to say is, well, if we're going to enumerate and eventually classify some up to some size of motifs, we need to think about metrics, right? We need to think about what numbers we're going to assign to these motifs and how we're going to kind of chart the motif landscape. And I would say,
let's just make sure I understand. So, for instance,
yeah,
when we're trying to assign, say, algorithmic complexity to a rule,
yeah,
we will want to, one, use motifs. So we're saying, okay, you're some mapping from one motif to another motif. Then the question is, well, how do those properties change, right? Because that's what you really want to examine. So those are the kind of metrics you want to assign to motifs, because you want to understand how under rewriting that metric is basically you want to be able to compare the left-hand side and the right-hand side.
Exactly. Basically,
and you're comparing motifs and you're comparing the metrics on these motifs.
Exactly.
Great.
Yeah.
Makes sense.
Exactly. So the metrics. So exactly. So you want to basically attach numbers to your motifs, and this is done, by the way. This, for example, this graphic in particular is an example of assigning two kinds of numbers. So one is size, which I'm calling the number of edges. These are always connected, so that's why it makes sense.
Sure.
And then these red numbers represent what I called externality, which is just the number of vertices that are kind of dangling, right? So the definition is the vertices that have the common lowest degree, right? So if all the vertices have the same degree, there's no lowest in that sense. So there's no external. But anyway, so this is two external, right, by convention. This is two external because this has degree 2. These two have degree 1. This has 0 because they all have degree 2. This has degree 2 and degree 1. This has degree 3 and degree 1, and so on. So basically, the number is measuring something that is entirely intrinsic to the motif, right? And so this is just an example of what I call here distribution of connectivity, for example, right? This is basically a distribution of degrees. And it allows you to, because of the distribution of degrees, it allows you to say, well, I then count the number of vertices that are external in this definition. This is just an example. I'm not saying this is particularly relevant or particularly important, but as an example, it's a way to, given a distribution of degrees in your hypergraph, you can assign a single metric. So there's a huge range of possibilities here, and this is something that we should probably meet Nick tomorrow or whenever we find some time and actually discuss in specific details of how we're gonna build this and how we're gonna what is easier, what is harder, and so on, because there's so much. I mean, the obvious ones obviously are the aggregate metrics, like overall size, graded order. You can grade everything by order, right? Like you can grade the number of edges per order. You can grade everything, but these are the aggregate kind of boring ones. And then we can get into the more graph theoretic metrics, right? That look at connectivity distributions, centrality distributions, and things like that, right? Then of course there's possibilities of physics project related stuff where you interpret your hypergraphs like this space or space-time models that we've had. Again, I'm not so experienced with that, but this is perfectly reasonable because at the end of the day, it's going to be intrinsic to the hypergraphs anyway.
So my initial reaction is, if we pick one single metric, we'll run the risk of making an arbitrary selection.
Yeah.
If we attempt to bundle together every possible metric that we can imagine, we'll run the risk of performing measures between like the left-hand side, right-hand side of our rules that accounts for so many factors that we won't see significant changes, because one thing will change significantly, but it'll be something else that changes in the opposite way. And I think if we account for too many things, it won't be terribly informative. No matter what, our measures will use these metrics on motifs in order to approximate the algorithmic complexity of the rule or the kind of built-in ability to perform non-trivial computational work that the rules allow for.
Yeah.
I think no matter what, it will be something of a proxy. We can, what I would recommend is we bundle together some of these metrics. We make some argument as to why we've chosen these in particular, why we haven't decided to bundle in further ones, and then we'll have to come up with some way to account for several of these at a time when we're comparing the hypergraphs on the left-hand and right-hand side of the rule. That sounds reasonable.
Yeah,
right?
yeah, yeah. So by the way, I should have clarified that metrics are intrinsic, right? So these are things that, I mean, I just listed the possibilities that we have for intrinsic properties of hypergraphs, right? So this is when we look into the next sections that are much more open-ended right now, and this is really something we should define, is getting into the complexity is where we're going to make choices. Like in the metric part, sure. I mean, these things are kind of for free because these are canonical constructions that you do, right?
Sure.
In the complexity side is when we start to make non-trivial choices. For example, saying,
I agree.
Let's try and generalize spectral theory, and which is not obvious how to do in this higher order world. Once you have some version of higher order spectral theory, then you can just say, well, von Neumann entropy makes sense, and let's run with it, right? So the choices made in the complexity level are much more obviously choices. In the context of metrics, is more about what you want to emphasize about your motifs, right? It's just a matter of what information are you extracting that is particularly interesting. So yeah.
And by the way, we need not be dogmatic about this. We could write a report in which we consider different bundles of metrics. And we could even create hypergraphs where we're attaching information based on different approximations. I'm in no hurry for us to create some, definitive branded complexity measure like the Pata Karatala, measure. There's no need to do that. We can just come up with a number of these that seem reasonable, and over time, as we continue to apply it, we'll probably, develop a few favorites. So not even one.
Yeah. So James, just to contextualize something that we were discussing earlier today, is that the reason why I was presenting this algebra in arrays, right? All these details that are kind of pre-computational, this kind of background structure that is there to exploit.
Yes.
The real reason is that von Neumann entropy from spectral data is the go-to measure of complexity in graph theory, right? In network theory generally, it's one of the main interpretations that people use, and there's a lot of work done in this sort of spectral approach to graphs, and there's operators and discrete operators on graphs and all these kinds of things. So the issue is that we don't have a spectral theory of higher order arrays. We just don't have it. Like, as a mathematical community, it doesn't exist, right? There are some attempts here and there. There's some advances, but there isn't a well-developed spectral theory for this higher order stuff. So understanding that we are in a context where we need to make choices and we need to push into directions that have not really been spelled out in the literature is something that I think is important, because we can always collapse back to binary graphs. I mean, we've seen all the literature. We've seen the many papers that just do that. Like, they do this order reduction, and they do some adjacency matrix and things like that. But if we want to be original and contribute something that is likely to be novel and is likely to be kind of orthogonal to other directions that people have done in the past, I would say that having a kind of incisive novel approach into this higher order spectral theory, which a prerequisite of which is understanding a little bit what you're doing compositionally, because that's what it means to do algebra, right? Linear algebra in the spectral theory. It's necessary, right? Like, we need this as a kind of preliminary step. So that's why, I mean, I don't have a passion to just spend hours and hours and days and weeks in just delving into the algebra of these higher array matrices. I mean, because that's a vast universe, infinite universe, who knows what happens there. But I do have a sense that if we are going to talk about von Neumann entropy approach to complexity of hypergraphs, we need to have a sense of what this higher order compositionality is doing. And so just context for the previous thing.
That's very helpful, right? So on the one hand, there are a few aspects to this study. And one thing that we can always keep in mind I was speaking with Wukash about this on a different matter related to Langlands, is, we're an institute. It's not as though fellows are on contract to do one particular study. We can do one study that is encapsulated within some report, and we can always speak to the next steps that have to be taken in order to advance the study further. So for instance, we could set this complexity categorical framework up with the specific objective of making more precise these discussions about emulations that we've had. And we could, as a temporary measure, for instance, this is like a hypothetical, as a temporary measure, we could include different proxy measures. And we could say, what we would really like to see is the development of a von Neumann entropy measure for these particular graphs, which does not exist. As soon as we identify an objective that's that specific, the real thing to do there is to begin to contact people who are, there are probably people who are working on this.
Yeah,
there are probably people
some,
who
yeah.
are, and you know some. So if that's, I would say, Wukash is a similar thing where on the one hand, there's this kind of general treatment of computational Langlands, and then on the other hand, there's this more specific push towards ever more sophisticated automated theorem proving. And it's like, we can always disaggregate these projects from one another and make several distinct kind of modular efforts that contribute towards some cumulative effort, right? Because I would hate to see, for instance, if we made progress in a number of these areas, we have reasonable work to show, but then it ends up taking, suppose it takes like 10 months of really hard work to come up with this von Neumann entropy measure. It would be a shame to put everything else on the shelf just in order to get that. Now, I have no context about the status of this measure for, say, the kind of graphs that we have in mind. So if this is important, especially if it's like, the point you're making is that this is a way to suture what we're doing to kind of standard practices amongst, say, the graph theory community. And if it turns out that what we need also happens to be an object of research that other people share, then this is a good opportunity for us to interact with potential colleagues. Yeah. So, but rather than us try and do it alone or in isolation, we should start having conversations with people. So if you know people, Carlos, who are interested in this, and we can begin to understand like how much progress is made. Are there people who have like they almost have a preprint, they almost have some attempt, or like attempts have been made and people are arguing over it. There are like many different ways in which outstanding problems, there are many different, like the status of an outstanding problem certainly varies. So I'd like to know more about the kind of the status of that.
I'll contact some people this week and I'll bring you a picture, like a 10-minute picture of the status quo of the field next week.
Yeah, we could have a stream with some people. Why not?
Absolutely.
Let's let von Neumann bring people together, right?
Yeah, absolutely.
We can all band together under the banner of Janos, right? Yeah. Absolutely.
Anyway, so that was kind of the to see the context of why I'm making effort into the arrays and the compositionality and so on.
I see. Okay.
Yeah.
Got it.
Because there are other aspects.
That's the real reason.
Yeah. This was coming there, but there are other aspects that I didn't mention. So, for example, there's another. So so this was all kind of intrinsic for hypergraphs, right? There's a big effort. There's just kind of intrinsic for hypergraphs, right? Which I think it's intuitive to imagine that once we really have that pinned down, label hypergraphs should just be an elaboration of that, because really label hypergraphs is just some maps over these hypergraphs and there's not so much complication there. So now the other aspect, of course, is the dynamical or computational or rewrite aspect of all of this, right? So so there is the very obvious, so one could ideally think that if we understand the data structures well enough, then doing rewrite theory over them or rewrite systems over them should be, just a matter of, doing rewrite theory and doing finite examples and computational experiments and so on. But the fact of the matter is that there is a large community, relatively large, it's not huge by any stretch, but relatively large community of people who have been working on hypergraph rewrite systems for the last 5, 6, 10 years at most. And it's relatively active. And I've mentioned this a couple of times before. I don't think that at this stage we need to push a lot in this particular direction. I don't think we need to because otherwise I will have to spend days and days and days just studying this stuff and working on this, and sinking a lot of time in that, which is not a bad thing, but I don't think it's the top priority right now, because if we have a good enough framework for the hypergraphs themselves, I think the rewrite theory is going to come more or less naturally, and it will be much more interesting a bit further down the line. When we have those, when we have some examples of rewrite systems, to actually go check the literature, invite these people and say, oh, what do you think about this? How does it fit in your landscape of categorical rewrite systems and so on? So that's what I envision this categories section will be. It will be kind of a summary and pointers for experts that can actually references to all this literature that I'm mentioning, to all these people who do graph rewrite systems, categorical rewrite systems, and to have a sort of a point of connection with them. But at the moment, I don't think we are ready to export their technology, so to speak, and bring their technology, their mathematical technology into our research, because I think they are too far removed from the concrete nature of the objects they deal with. Right, because that's what category theories do. It's kind of the art of category theory. So that's maybe and so what I imagine the rewrite part to be is, as I say here, is sure we can contextualize what we do in this push-out categorical formalism, which is very standard and quite easy to understand. And so we can actually try to double this part of the document as a more pedagogical, more accessible introduction to this particular formulation, which I struggled a lot to understand for the first time, because I couldn't find like a single kind of 2-3 page digest of this is what it is. There's mixed in 90s papers and early 2000s papers and here and there. So that's one side. But the other thing is we can have this actually implemented in Wolfram language and do all the kind of experimental mathematics that we propose there, right?
There's just one detail, which is, so when we have the final report, the section on categories will begin largely as a review, but then we are attaching new data to these categories concerning the complexity involved in passing from one hypergraph to another.
Let me because maybe the naming of the section, because this is completely temporary, it's not final at all. Like that. Because that's something that we have to define, something that we have to invent, right?
Yeah.
So So the thing is, when I mentioned categories here, as I said, is this point of contact on identifying what categories we work on, and then moving in this, because
if by definition it's a review section, then it's going to consist of review. It'll be
it's not only a review section. It is a section where we identify the categories that we're working on implicitly.
Yeah.
Right. So when we define our morphisms for hypergraphs, our classes of hypergraphs, the types of hypergraphs that we want to focus on, and so on, these will be hopefully shown to be subcategories of some natural category of hypergraphs and things like that. So that's what I imagine for that, and a lot of the constructions are going to find that categorical formulation. That it will be very helpful to make contact with all this, especially this people I'm going to see in Glasgow, all the community of category theorists. If they have a section where they can, read category theory that talks about the stuff that happens in the rest of the document, they can basically ignore the rest of the document for all they care, probably, but they can get some point of contact with the category theory, right? And I think that's kind of building like a sort of a categorical API with the category theorists, right? It's kind of that philosophy. Now, when coming up with this idea of introducing complexity, a relational notion of complexity that you've mentioned before as attaching complexity data to morphisms. I mean, there are many possibilities, right? I think that needs to come in that's what I imagine the complexity section to be. I imagine the complexity section to be the most sort of original and the one that actually sort of puts forward proposals, things that are new, things that kind of don't exist, right?
That's fine. I mean, to present a section that is familiar and recognizable to particular research communities as a kind of a point of entry, that's a good idea. Yeah, that's fine. And to have a distinct section that showcases the new inventions. Yeah, that's fine. It's very neatly organized. I have no problem with that.
Sure.
Yeah.
And finally, then computation. It's where we kind of have a summary of all the implementations that we do. You know, if Nick is working on this backlit and all these encodings, I think it's very relevant that. I mean, and again, this is in no particular order, by the way. I mean, the order here is completely spurious. I mean, I guess I did put the introduction definitions at the beginning and the more advanced stuff at the end, but whichever order fits best.
So this is kind of a technical document on the hypergraphs and with extensions to other topics such as category theory and these new complexity measures. But we'll also have some other, you know, we can write some other additional report. And what I'd like to see that report include is, you know, some combination of initial experiment, like having a report that we do that includes both experimental mathematics and formalism will be very refreshing, because I mean, what I kind of like about the arc of this study is that it began with experiment.
It
actually began with computational experiment, and then that motivated this greater theory building effort, which will also be made computational in turn.
Yeah, I'll just bring this page up because this is experimental. Just to, it's already in, like this is. I mean, this is enumerative, maybe not so experimental, but it is making a point that is purely conceptual about the numbers that were generated, which is the fact that the cardinality of these ISO classes blows up when you go up in order, right? And I mean, the intuition is that as you go up in order, I only checked for 3, but is that this grows much faster. So no, absolutely. So I'm just saying, I agree. I completely agree. We'll absolutely. I mean, have this experimental, but that's why I wanted to. So we'll probably meet tomorrow. First time that we have time, Nick and I and Richard, if he's available, to start deciding, okay, what kind of hypergraphs we want to look into, how we're going to implement symmetry if they are undirected, and all these kinds of details. Because as you say, we are ready to basically run a lot of this. I mean, little experiments and start counting stuff, start doing nice plots, like, you know, all these taxonomy things we can start to do, because this is very nice basic functionality.
Yes.
So yeah.
Well, yeah, this is great. I'm very glad that you wrote up this report. This is exactly like the kind of thing that I like. So now we have, I mean, this is not still fully planned, especially because the sections at the end are still brief, but we can just build upon it. Yeah. We'll have discussions, and this is to serve as a, I mean, this document will incorporate ideas and plans that we make, and it will continue to grow. So this is good. We've basically run out of time. We were going to discuss some of the work that Nick did, but didn't.
Do you want to show something quick, Nick, or do you have to rush off, James?
I have to jump on a call in 1 minute. So unless Nick is fat, I don't think we have.
We can leave it for the next time.
Yeah. Leave it for the fuller version.
All right, guys. Well, I'm glad we had this follow-up. This was very helpful. I have a pretty clear understanding of what you've done and where we're going next. So thank you very much, Carlos. Good job.
My pleasure.
Nick, Richard, see you guys soon. Cheerio. Bye-bye.
Goodbye.
Thank you.